Lattice sieving is a technique for finding smooth values of a bivariate polynomial f a b f a b closing curly bracket over a large region. It is almost exclusively used in conjunction with the number field sieve. The original idea of the lattice sieve came from John Pollard. The algorithm implicitly involves the ideal structure of the number fields of the polynomial. It takes advantage of the theorem that any prime ideal above some rational prime p can be written as p z alpha plus u plus v alpha z alpha display style p mathbb z alpha plus u plus v alpha mathbb z alpha closing curly bracket. One then picks many prime numbers q of an appropriate size, usually just above the factor base limit, and proceeds by, for each q, list the prime ideals above q by factorising the polynomial f a b over g f q display style g f q closing curly bracket for each of these prime ideals, which are called special q display style mathfrak q s construct a reduced basis x y display style mathbf x mathbf y for the lattice L generated by q display style mathfrak q. Set a two-dimensional array called the sieve region to 0 for each prime ideal p display style mathfrak p in the factor base. Construct a reduced basis x p y p display style mathbf x underscore mathfrak p mathbf y underscore mathfrak p for the sublattice of L generated by p q display style mathfrak pq for each element of that sublattice lying within a sufficiently large sieve region. Add log pipe p pipe display style log mathfrak p to that entry. Read out all the entries in the sieve region with a large enough value for the number field sieve application. It is necessary for two polynomials both to have smooth values. This is handled by running the inner loop over both polynomials, whilst the special q can be taken from either side. Treatments of the inmost loop. There are a number of clever approaches to implementing the inmost loop, since listing the elements of a lattice within a rectangular region efficiently is itself a non-trivial problem, and efficiently batching together updates to a sieve region in order to take advantage of cache structures is another non-trivial problem. The normal solution to the first is to have an ordering of the lattice points defined by couple of generators picked so that the decision rule which takes you from one lattice point to the next is straightforward. The normal solution to the second is to collect a series of lists of updates to subregions of the array smaller than the size of the level 2 cache, with the number of lists being roughly the number of lines in the L1 cache, so that adding an entry to a list is generally a cache hit, and then applying the list of updates one at a time, where each application will be a level 2 cache hit. For this to be efficient, you need to be able to store a number of updates at least comparable to the size of the sieve array, so this can be quite profligate in memory usage.